Hey everybody, this video is going to go through the guided notes that were given to you on your last in-person day that I said were for Friday. I just want to talk a little bit about applications. This isn't the main part of today, and you did see some of these in your Khan Academy assignments, but common applications of quadratics are something called launched objects, the very common one. Let me show you this picture I drew before. This is someone, let's say, shooting a basketball. Common parts of these graphs of quadratics that are important to us with launched objects is the y-intercept, meaning when was the object released? That's going to be our y-intercept. The vertex would be the maximum height of that object, and the y-intercept, or sorry, the x-intercepts here would represent when that object hits the ground. These are the most common things we'd be asked for in a word problem. There's other instances of quadratics in real life, archways, bridges, half pipe. I mean, there's so many applications of quadratics. Just one of the common ones here is a launched object. In any case, though, the vertex, y-intercept, and x-intercepts are usually the points we're really most concerned with. So here's an example. This is what you have in your notes. The graph shows the height h in feet, so the y-axis here is height, of a small rocket t seconds after it's launched. The path of the rocket is given by the equation h of t equals negative 16 t squared plus 128 t. So this is a quadratic, obviously it's squared, where the x is time. So over time, how high does this object get? So you can kind of picture this, like when it's launched, it's rising, 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 rising. It meets some reaches some maximum height, and then starts to fall down. So this is not horizontal distance. This is over time. So as time goes on, the rocket will get to a maximum and then fall down. My question's about this situation. What is the greatest height the rocket reaches? So how high does it go? And if you look at this graph, it looks to be about 260. So by looking at the graph, I have a roundabout answer of what it is, about 260. But I can actually find that y value. Right, this is in standard form, so I can actually find the vertex. So if I were to find that vertex, I would do negative b over 2a. So here that's negative 128 divided by 2 times negative 16. I could do that real quick. Or you can do it in the calculator, the whole thing. So negative 128 divided by 2 times negative 16. I'm going to put both of those in parentheses here. And I get 4. So it takes 4 seconds. That's what this means. 4 seconds to get to its maximum height. Now to find the height that goes with that x value, I'm going to plug that 4 in here for t. So I have negative 16. Instead of t, we're going to put 4 squared plus 128 times 4. And press enter. So the actual maximum height here is 256. So it takes 4 seconds to get to a maximum height of 256. That's what the vertex in this situation means. I'm going to write that down quick. And the next question asks about how high is the rocket after 1 second. So again, I can look at the graph. Like if I look at the graph, I go over to 1 second. It looks to be about 100. But I can actually calculate that since I have the function. At 1 second, the time is 1. I can put a 1 in for t. So again, I'm just going to do it in my calculator. Negative 16 times 1 squared plus 128 times 1. That's just 128. I'll put it there anyway. And I get 112. So the graph looked to be about 100, but the actual value there is 112. And then domain and range here are kind of interesting because this is cut off, right? The rocket's not going to infinity. So my domain, my x values, the smallest x value here is 0 at the origin. The highest x value, or the end of the domain, is going to be at 8. And the range works the same way. Again, I don't have infinities here. So the lowest y value is 0, right? The x-axis, y is 0. And the highest it goes is the maximum here at 256. It could have asked me other questions. I mean, those are the parts I gave you here, but it could say how long till the rocket hits the ground. You would say 8 seconds, right? Right there is where it hits the ground. Let's look at one more. This one doesn't have a function along with it. It's a swim team member performs a dive from a platform. The parabola shows the path of her dive. So let's look at my axes. So here, this is appearing to be both distance, right? So the x-axis here is this person diving off this platform is the horizontal distance. And this is the height. So let's go ahead and answer these questions. I don't think you have a part D in yours. So let's just answer A, B, and C. How high was the platform that she dove off of? Well, I look at this. This is the start, right? So the start of her dive is right here. So it looks like 14 feet. And that is the y-intercept. Oh, I just said the next question. That's the y-intercept. And the axis of symmetry goes through the vertex. It looks to be 3 feet. X equals 3. And you don't have a part D. So I just wanted to show you a couple applications of these graphs, what they look like. We'll be doing more applications in the next unit on solving quadratics. The main goal of this Google Meet, or this recording, is to talk about quadratic inequality. So with quadratic inequalities, it's going to look like graphing the same thing, but instead of equals, we're going to have inequality signs. So either less than or equal to, greater than or equal to. And just like we did with linear inequalities, we have to think about two things here. We have to think about the boundary line. That's the parabola itself, the U. Now, is that U going to be solid or dashed? What's going to decide that for us is whether there's an equal with the inequality. So if there is an equal with the inequality, we're going to connect the points of our parabola with a solid line. And if there's not an equal to, we're going to connect them with a dashed line. The other thing we're concerned about is shading. So remember, when we did these before with linear inequalities, we either shaded above or below. Same thing here, but it's just a U-shaped graph. So we're going to shade above the parabola. That could be inside or outside. If you look at my pictures here, above, if it opens up, ends up being inside. Above, if it's upside down, ends up being outside. So think about like whether you have a bowl or a roof or an umbrella. Like where would the water fall above? If it was above the bowl, it would fall in the bowl. If it was above the umbrella, it would fall on top of the umbrella. So think about what that shading above means. And then just the opposite, if it's a less than or equal to, we're going to shade below. Now your assignment that you'll have to submit today is the back of these guided notes. And I'm going to go ahead and do questions 1 and 2 with you in this recording, just so you see 2 examples, and then you only have 4 for homework, or four to turn in today. So here's my first quadratic. It's in standard form. I quickly find the vertex. You should know how to find the vertex by now. If I do negative b over 2a, that's negative 8's positive 8 divided by negative 2 is negative 4. So my vertex is at negative 4. And then if I plug that in there, I get negative 16 plus 32 is 16 minus 17 is negative 1. So there's my vertex. And my axis of symmetry is at negative 4. And if I build a table of points here, and we think about these points, if I plug these in at negative 5, I'm going to get negative 2, I believe. And at negative 2, I'm going to get negative 4, I believe. Let me double check that. If I plug in a negative 2, That's 4, make it negative. Negative 4 plus 16 is 12. 12 minus 17 is negative 6. I'm a little bit off here. All right, and if I plot these points just like we did before, so far we graphed it just like you did on the last quiz, but here, when I connect them, I need to look at the inequality. This inequality in number 1 has an equal to, so that means I'm going to use a solid parabola to connect them. And then the inequality is greater, so I think, well, where is the quadratic greater here? Well, it's greater above. If it's greater, I shade above. So above the quadratic ends up being right here. So there's my solution to this quadratic inequality. Any point in this yellow shaded area satisfies that inequality. The next one's going to work the same. I'm going to pause this. I only have a max of 15 minutes. I'm going to go ahead and fill in the T-chart and the vertex and axis of symmetry. And then we'll kind of look at how the shading and lines are different. All right, so I just paused recording for a second. I went ahead and found the vertex, found the axis of symmetry, and found the table of points, just like we did on the quiz you took your last in-person day. But now when I go to connect these points, I look at the inequality. If there's no equal, here there is no equal, I'm going to connect them with a dashed line. And the shading is now less. So less, I think about, I want to shade below this quadratic. So below on this one ends up being down here. So there's my solution for this quadratic inequality. So your homework is to finish 3, 4, 5, and 6 and submit that via Google Classroom by 3 p.m. today or Friday. Thank you.